Hello Math 125 students. I'm going to make a video where I quickly summarize 7.3 and then I'm going to do a couple homework questions because there are some big problems there, so I thought I would give you a few additional tips. One note is before you do the homework, you really should print off the unit circle, my little from my website or elsewhere. Print off the integral table, the full integral table with all the integrals I've given you. And then you should review the lecture. So if you've forgotten where those things are, let me pull it up here quickly. So if you go to my materials page, you can see you can also see my lecture notes on Canvas, but you can see the old lecture notes, and you should have this three-step idea, which is given this in a situation, you do this substitution because this certain identity appears. Right? If it's x squared minus a number, you're going to use secant. If it's a number minus x squared, you're going to use sine. So if you don't know all that, that's the reviewing the lecture part. Once you do the substitution, the radical goes away, and you're left with a trig integral. And then you need to use the methods from 7.2 to solve. This is an example we did in class. When you are done using the methods from 7.2, then you draw a triangle using the original substitution, and that triangle helps you figure out what the other trig functions are. There are more examples in my notes. Okay, so it's this three distinct things. If you're having trouble, you need to identify where it is, because you substitute, you do a trig integral, you use the triangle trick. The things you really need to print out are my units, this unit circle. This is just going to make you faster. So if you have this out, you're going to be able to more quickly get the exact values. It's just faster than looking things up or doing a calculation. Everything you need is here when it comes to trig in this course. The other thing is our full integral table, and that includes the few new integrals that I've given you, these ones down here. There are times when these happen, so before you start integrating a whole bunch, make sure it's not something I've already given you. Okay, and again, the things we need are all here. So at this point, you really should print off those couple things and be ready to go. So what I'd like to do in this video is just do a few problems because they all just take some time, and so I only can do so many in class. I will do a few more in my next lecture, but let's peek at the homework. And we're going to do some homework questions. Hopefully this is helpful to kind of summarize. So anyways, I don't think I'll do this one. I'll leave this one to you. Do the substitution. Interestingly, this one can be done without trig substitution as well, but it's a chance to practice. So after you substitute this in, let me get my pen out. This should all simplify. The square root should go away. The whole point is if there's a plus, we want to use tangent. The reason there's a 6 is so that when we square, we get this. So the whole point of the entire section is that this will become this. If you didn't catch this, plus 36. And the whole point of that is then you can factor out a 36, and it becomes tangent square root of theta plus 1. And the point of that is that's the same thing as secant squared. So you get the square root of 36, secant squared of theta, so you get 6 secant of theta. And then you keep going from there. Let's look at this one. So let's look at question 2. Simply because some students were asking about that in office hours, and it also has bounds. I will do something in class with bounds, but this allows me, because I'm making a video, I can spend a little more time. One positive about a problem with bounds is you don't have to switch back to your original variable if you change the bounds as you go. In this problem, I do think it is much easier if you change the bounds as you go. What do I mean by that? Let's take a quick look at the problem. I don't know if I can fit this very well. Let's come over here. Let's give myself some more space. Maybe I'll do a quick snapshot here. If it'll let me. I grab this. And just give me a moment. Okay, let's come over here and work on this problem. So what I would do, so first you should see that it's a t squared minus 4. In that situation, the identity that is similar is this. This is how I remember it. Of course, you can also just use the table. Is that secant squared of theta minus 1 is equal to tangent squared of theta. Again, this is easier if you already have the trig identities in front of you, if you have the unit circle in front of you, if you have the trig integrals in front of you. So that's why I encourage you to print those things off first. Now we're going to substitute. The whole point of this is if I make the following substitution, t equals 2 secant of theta, then this identity will appear. But if I'm going to do that, I have to change a few other things. So the whole point is that this thing, this t squared minus 4, is going to become the square root of 4 secant squared of theta minus 4. And again, the whole point of that is then you can factor out a 4. It's going to become secant squared of theta minus 1. And the whole point of that is it's going to become 4 tangent squared of theta, which is 2 tangent of theta on the appropriate domain. There's a little subtlety if you want to read the text about, what if tangent is negative. So we're restricting it to when it's positive. You can read more about that as I said on there, but we're going to leave this for now. And that depends on the bounds a little bit. So there is a comment, I'm going to talk about the bounds in just a second, but this is 1 over 2 tangent of theta. So that's the point of the idea, is that this happens. The rest of the stuff is dealing with the consequences. So one consequence is that you have to take the derivative, and the derivative is secant theta, tangent theta. At this point, you really need to know these derivatives. They need to be memorized, but again, if you have that calculus fact sheet in front of you, you would have it right there. So this is 2 secant of theta, tangent of theta, d theta. And then lastly, you can't forget this t cubed. T cubed would be this cubed. 2 cubed is 8. This would be secant cubed of theta. And then lastly, the bounds. So this is a good example of it is worth your while to change the bounds because I think it makes it easier. If you don't change the bounds, then at the end of the problem, you're going to have to do the triangle trick, which works, and then you change back to your original numbers. But if you change the bounds now, it actually makes the rest of the problem a lot easier. And what I mean by that, I'm going to use a different color so you can see it. It's a little bit of work to change the bounds. I'm not as picky about this. I usually don't take off points here if someone doesn't change the bounds. But I just want to make a point of, they gave me t equals 4. And whether you do it now or do it later, you're still going to have to do it. Unfortunately, it's a bit of solving. And sometimes students go, well, it's a secant, I don't know how to solve. But if you just take a moment here, then it's going to make the rest of the problem easier. This is the same as saying, when is cosine equal to a half? You say, well, I don't know what that is. You should. I want you to know what that is. But if you have this in front of you, you have it. Cosine is the x-coordinate of the unit circle. So the first time when cosine is a half is pi over 3. It's sitting right there. So if you had this in front of you, you would immediately know. When is cosine a half? Pi over 3. Done. That's what I mean by that is faster than searching for things or getting the unit circle tells you all your trig values very quickly. I think sometimes people don't realize this. So if you had printed that off, you would immediately say pi over 3 and you'd have the exact value. Okay, similarly with t equals 2 root 2, you could say and I'm just plugging in right here. Everything we're doing is driven by this. Sometimes students forget that we know the substitution. So this is 2 secant of theta, which is the same as square root of 2 is secant of theta, which is the same as cosine of theta. This requires a little bit of ingenuity if you've never seen this before, but 1 over square root of 2, you might say, well, that doesn't look familiar. But there is something that is familiar, which is square root of 2 over 2. And if you multiply top and bottom by square root of 2, this is square root of 2 over 2. Sometimes that confuses people, but these two things are the same. If you do enough of these problems, you want to be able to recognize that. Anyways, that's theta is, you probably know that one, pi over 4. But if you don't know, then you'd look at the unit circle. Again, the answer is there. You'd be asking, when is the x-coordinate? The x-coordinate is the cosine. So when is the x-coordinate square root of 2 over 2? It's at pi over 4. There are other solutions, but you wanted to choose 2 consecutive solutions, meaning I probably wouldn't pick 5 pi over 3, 5 pi over 3 and 7 pi over 4, even though you could. I'll pick the first 2 solutions. All right, so that's it. So that was a little bit of extra effort. So yes, that was kind of bad, but not really, because now we are done, and we don't have to do the triangle trick. So that's the main thing I want to comment on this problem, since I hadn't done one in class yet with bounds. But the point of that is now we can simplify this. We can take out one of the secants, and we end up with 1/8 the integral from pi over 4. And there's no reason to change back. So if there are bounds, you don't have to do the triangle trick, and it's 1 over secant squared of theta d theta. And then we have to think about what to do. So then we switch gears back into integrating things of this form. And you should recognize that that's the same thing as cosine squared. And you go, it's even. In 7.2 we said, well, if it's sine and cosine and there's only even powers, then we better do the half angle identity, 1 plus cosine. So this is where you really need those strategies from 7.2, because this builds on it. And then you just keep going. So this is 1/16. Like we don't have no triangle trick is needed in this problem. And now it's time to integrate. Quite a few people forget to integrate. So don't forget to integrate. 1 becomes theta. Cosine becomes sine. And there should be a 1/2. And if you can't remember if it's plus or minus, again, you have because you printed off the calculus fact sheet and the trig fact sheet, they should be sitting in front of you as you do this homework. Okay, so then we're going to evaluate from pi over 2. So if you had not changed the bounds, now you would have to do the triangle trick. And you'd have to use those tips from class, which is use the half angle identity there, do inverse secant. I'm avoiding all of that. And so this is going to be 1/16 pi over 3. You don't need to change back because I already changed the bounds. So this is once again the point I'm making here. So your final answer is this minus whatever this is. Pi over 4 plus 1/2. And apologies if I have any typos or anything. I'm trying to give you the idea here. I'm just doing this on the fly. But I hope this gives you the idea. So anyways, then you go, well, I don't know what sine of 2 pi over 3 is, and I don't know what sine of pi over 2 is. Again, those are sitting right in front of you if you've printed the things off. Sine of 2 pi over 3 is right here. It's the y-coordinate. It's root 3 over 2. See how fast that is? Root 3 over 2. And the other one is sine of pi over 2. Sine of pi over 2, sine is the y value, 1. So root 3 over 2 and 1. So I think people have the wrong sense. The unit circle is not something we're trying to say, oh, you need to do this extra work. It is faster. So pi over 3 plus, we said this is 1/2 and this is root 3 over 2. And then minus pi over 4. And then this thing is minus 1/2 if I distribute the minus. And you can clean this up a little bit, but not much. You're just going to type in this big mess. You can put the two terms with pi together. All right, I hope that's helpful. So that was one where you got to see the whole method, except I didn't do the triangle trick because I didn't have to. So that was just something with bounds. So there's problem 2. Hopefully that's helpful. Other comments from office hours that people had on a few of these questions. I think I will make a separate video about 5, 6, and 7 just to keep this video short. I've had quite a few people ask me about this problem in office hours right here. And the problem is the 25 is throwing people off, but ultimately it's the same idea. You can do this in one of 2 ways, and I like them both. You could write it as 25. So whenever you are bothered by a coefficient not being 1, just pull it out. But you do have to adjust and make this 1 over 25. And then you'd have to do x is 1 over 5 sine of theta. And that will work fine. This comes out exactly like the last example from the last lecture. Or, the way I probably would do it, is I would think of the original problem like this. 5 is a little bit more clever way to do it, to try to avoid fractions. And then I would say 5x is equal to sine of theta. You can see that both these things are the same. So both these approaches are the same, but this makes it a little easier to plug in because this would be the integral of the square root of 1 minus sine squared of theta. So you avoid some fractions. But when you take the derivative, you are going to have a 1/5 cosine of theta d theta when you take the derivative of this. It's going to be 5 dx is equal to cosine of theta d theta. So dx is 1/5. And then you keep going. This one is another example where it's much easier if you change the bounds as you go. This one will require, question 3 will require the triangle trick at the end because there are no bounds. But here's another situation where it's better if you change the bounds. And what I mean by that is if you say x is a sine of theta, it's actually really easy to change the bounds here. Because when x equals a, I have cats in the background. I don't know if they'll make an appearance, but they're making noise. They tend to not want to come over here. But you can actually figure this out because when is sine of theta equal to 1? That's when theta is pi over 2. That's the first time. When is x equals 0? Well, that's when sine is equal to 0, which is 0. So if I was doing this problem, I would immediately do 0 to pi over 2, and then I would change everything else, and then the triangle trick is not needed. Okay. I think I will just stop this video and do a separate one where I do one of these questions because it's a little bit different idea. But I hope that kind of sorts out some of the smaller things and just gives you another example. All right, let's stop at that and I will make another short video.